Let's talk networks. The world is basically composed of networks. You're probably connected to at least 6 or 7 right now. Now, the mathematical approach to the study of networks, at least the one I know, is called graph theory. The study of networks is extremely relevant in many fields of science and technology, electrical engineering, sociology, telecommunications, and also neuroscience, and specifically cognitive neuroscience. Researchers in this field try to describe, explain, and predict how the cells in our brain produce behavior. And as some of you might know, the brain is composed of networks. Let me first introduce you to the most popular research technique in cognitive neuroscience, magnetic resonance imaging, also called MRI. MRI scanners give you nice 3D reconstructions of the brain. It has been utilized for decades for the diagnosis of different brain pathologies such as cancer or getting your head drilled with an iron bar. MRI is used nowadays to detect the connectivity patterns between brain regions that come together as networks. This technique is called functional MRI or fMRI. Many researchers have found that the pattern of interactions between these brain regions are causally related to human behavior. Over the last 12 months, more than 35,000 fMRI studies were published in scientific journals. The resolution of fMRI is about 27 cubic millimeters, that is 3 per 3 per 3 millimeters. However, most of the research is done by analyzing the connectivity patterns between bigger regions in order to improve the signal-to-noise ratio. So we have a node full of neurons firing. But there isn't just one, there is a lot, and there is a bunch of connections between them. Even in this simple example network, there is a lot of variables to take into account. Nodes can have different sizes, and the edges between these nodes are variable in weight. Different subsets of nodes may be grouped together, conforming smaller networks inside the big network, and so on. Let's say you have a network looking like this. We will call it G for graph. This graph is composed of nodes and edges. As you can see, there is plenty of numbers to play around with, related both to individual nodes and to the network. Some of the properties that we can calculate for individual nodes are degree, which is calculated as the total number of edges connected to a node, strength, which is the sum of the weights of all edges connected to a node, path length, or the average distance from a node to a set of different nodes, or triangle, meaning the number of neighbors of a node that are also neighbors of each other. Now, based on these measures that are related to a specific node, we can calculate network level properties. Modularity is higher when a graph can be clearly divided into separated subgraphs or modules. Clustering coefficient is the fraction of triangles present around a node. Now, these are only some of the measures that you can extract from a graph, but there are many more, like global efficiency, local efficiency,
eccentricity, transitivity, closeness centrality, and between centrality, assortativity, within modules that score, small roundness, and participation.
Now, this method is great and everything, but specifically in neuroscience, we face a huge problem. It is believed that every single neuron inside our brain is part of a microscopic network, which is an object of study itself. So we have these nodes full of neurons and we analyze the connections between them. The thing is, each one of these nodes contains around 12 million neurons. So this is an example of a common network in neuroscience. It has 264 nodes. We could increase its resolution, assuming, for example, that inside each one of the nodes there is another network with 264 nodes. Yep. Let's do that one more time. And one more. Now we are in the neural level. Each one of the nodes here represents a single neuron. The thing is, each neuron is not usually connected to just 263 other neurons, but around 10,000. Oh, and each neuron's function is supported by around 10 glial cells that also play a role in this network communication. But I'm not worried about that. We'll get to the neural level. We're still trying to understand the functioning of the first network we talked about. Neuroscience has never been as successful as it is today in creating links between biology and psychology, between the mind and the body, between brain and behavior. Eventually, we'll get to the neural level, and graph theory will help us understand the role of individual neurons inside both microscopic and whole brain networks.